Thank you very much, Adrian, and thank you for setting this up. I've been now in CENTRA for a couple of weeks. This is the second week, and I'm very happy. It's been a very productive period. This one is super nice. And today I will talk about part of what I did in my PhD. And, the work I will talk about will be basically some work with Pulsar Timing Arrays. But in general, these experiments were conceived to look at astrophysics in general. So to try to understand if there is an underlying population of supermassive black holes, binaries, what's going on, what's their properties. Here I want to give you a different perspective and show you that these instruments that were originally built for astrophysics can be also useful if you want to do something else. So if you want to study dark matter or also modifications of gravity. So I am Clemente Smarra. I'm a PhD student in SISSA in investigation. And yes, that's the title of my talk. Yeah, okay. No. Okay. Check. Yes. Okay, so as for the outline, first of all, I want to give you like a very brief introduction of what pulsar timing arrays are. Really, what are we talking about when we talk about pulsar timing arrays, what they can do. And then I will focus on how it's possible to keep constraints on interplanetary dark matter, which is a specific candidate of dark matter with pulsar timing. And in particular, in order to do so, I will focus on three different cases. The first case is the gravitational coupling case. So where ultraviolet dark matter just interacts gravitationally. This is, in a sense, the most robust case, because if we know one thing about dark matter is that it interacts gravitationally. We don't know if it has couplings or not. But then I'm going to discuss in the following two parts what happens if dark matter indeed has an interaction, and if this interaction is a minimal interaction with gravity, or it has in general a standard model. And then I will shift to hopefully convince you that pulsar timing arrays can also be quite useful if you want to study modified gravity. And I will just present you with one such example, which is the case of Gauss formate. So let's get started. Yeah. Okay, so basically, what are pulsar timing arrays? First thing to understand is the word pulsar. So basically, pulsars are highly, very fastly spinning neutron stars, which emit a beam of radiation which hits us with a very precise period. So when we look at these pulsars are super precise and they send us a beam in a very precise fashion. And in particular, we are going to focus on millisecond pulsars. So it's this class of pulsar whose rotational period is of the order of a millisecond, and they have exceptional rotational stability. So they rotate, they send a radio beam. This radio beam is registered by telescopes. Then some stuff is done, and basically you can obtain a pulse profile. And this pulse profile turns out to be, after some manipulation, turns out to be very precise. So we can really look at this pulsar for 20 years, 30 years, and the pulse profile is remarkably precise. So in principle, any strange thing that you see in a pulse profile may be related to some phenomena that's happening, because if it were for the pulsar itself, the pulse profile would be always the same. So the purpose of pulsar timing arrays is really modeling the phase of the pulsar. So we really want to model the rotational phase of the pulsar, and the way you can do it is just by a simple Taylor expansion, where these are the derivatives of the rotational frequency. So it seems very easy, but actually in this formula, what appears here is the time of emission of the beam at the pulsar side. But we don't know that. We know the time of arrival of that beam at Earth. So our observable is not really the time the beam has been emitted from the pulsar, but it's really what we see. So we need a model, which is called a timing model, that allows us to relate what we see at observatories to the time of emission. And this timing model is very, very complicated. It's usually broken down into 3 different pieces. So there's one piece that deals with the transmission. So looking from the pulsar, there's one piece that deals with the transmission from the pulsar to the binary barycenter, if this pulsar is in a binary. Then there is a second piece, which basically deals with the propagation of this pulse beam, of this pulse from the binary barycenter to the solar system barycenter. And then a third piece, which is basically going from the solar system barycenter to the Earth, where we see the pulse. So we need really to model all the effects that happen here. There's a lot of effect related to interstellar dispersion, to the fact that the beam is traveling in a curved space-time due to the presence of massive bodies. There's really a lot of effects that influence the propagation time of this beam. So if we really want to do any inference, if we really want to study the time pulsar, we have to take all these effects into account. So as I was saying, we can write what is called a timing model, which is basically given by this formula, morally speaking, and it's a model that relates the emitted time, emission time, and the pulsar with the observed time at Earth. So we write down all the effects that we have in mind, atmospheric effects, interstellar propagation, and we write a timing model. So yes.
So the solar system effect.
Yes.
So is that the curvature?
There's many. One is one that you're mentioning. Then there are other effects also related to the presence of solar wind, for example, that influences the time of arrival of different frequencies of the radio beam, for example. So there's really the atmospheric effect due to the passage of the beam to the atmosphere of the Earth.
So the solar wind, how does it do that? The same distance speed of light?
Yes, basically yes. Yes. So if you look at different frequencies, they are going to accumulate different delays because one is arriving earlier and one is arriving later. So yes, but there's really a huge amount of them. But so in principle, if we are able to classify all these effects, we're fine. No, it seems there's a recipe. We just take all these effects, we classify them, and we fit, or we have this series of beams and the time of arrival. We fit this huge series of time of arrival with all the effects that we have. We're done. We have done everything. We can find the parameters of the timing model. Are we done? And no, the answer to this question is no. Once we do all of these, we are not really done. Because actually, if the timing model were super precise, we would be able to exactly predict when the next beam, the next pulse is going to arrive. So given our timing model with our best fit parameters, we could make a super precise prediction of when the next beam is going to arrive. We can do that, but then if we look at the observation, the next beam is going to arrive at a slightly different time. So what happens is that the following beam has this so-called timing residual, which is basically the difference between the observed arrival time of a beam and the time that I predicted using the best fit timing model. And it's really in this timing residual that people in Pulsar Timing Arrays community do science, because these timing residuals basically have incorporate all the effects that we have not modeled in the timing model. And these effects can be, for example, effects of pulsar noise. So the pulsar can have some strange features, maybe can have some glitches, it can happen. There are also measurement noises. We measure things and we make errors when we measure. But there can be also underlying physics. And very recently, there was this detection of the presence of a stochastic gravitational wave background permeating the universe. And this stochastic gravitational wave background would be in this class. So this is an underlying physics which we do not model in the timing model, but which affects timing residuals. So it produces an observed deviation in time of arrivals. And indeed, I mean, the detection of a stochastic gravitational wave background was the first thing that motivated the construction of pulsar timing arrays, which are basically network of millisecond pulse, are huge experiments which monitor a network of millisecond pulsars. So they monitor up to 60 millisecond pulsars. They monitor for 20, 30 years with a 1 week cadence. So basically, they observe this pulsar each week, or more or less, and they observe it for 20 years. And the idea was to find if there was indeed an underlying spectrum of gravitational waves. And how can we do that? As I told you, we have to look into timing residuals. This formula that I showed you here, we have to look into timing residuals. But in principle, in these timing residuals, there can be a lot of stuff, not just the stochastic background. There can be a lot of stuff. So we need to find a smart way to really understand how we can really disentangle the contribution of this background. And the idea is to correlate 2 millisecond pulsars. So if we take the timing residuals coming from 2 millisecond pulsar and we correlate, we can predict in general relativity how this correlation looks like for a stochastic background. And this correlation has 2 pieces. This piece here is like the power spectrum, the integrated power spectrum, basically, and this can be computed in general relativity. And there's this form here, or equivalent to this form here in terms of the characteristic strain. And then there's an angular part, which basically tells you that pulsars that are separated by an angle theta AP, those pulsars experience a specific correlation. If I change that angle, the correlation will be a little bit different. So by looking at a network of millisecond pulsars, then I can really disentangle the stochastic gravitational wave background from other sources of noises, which can affect, in principle, the timing residuals. And so the experiment, so Pulsar Timing Arrays did with data, and they found some results. So I was telling you before that basically in general relativity, we can predict what this looks like. We cannot really predict the amplitude because this depends on how many black hole, supermassive black hole binaries we have in our universe. So it's not really something we can predict. We can build semi-analytic models that give us an idea, but it's not a prediction in general relativity. But we can really predict the slope. If we assume that the binaries are circular and they emit through quadrupolar emission, we have a clear prediction of the slope, which is 13/3. So basically, we know that if you're looking for circular black hole binaries in general relativity, we should find something like this. So people did the analysis and they found something which is slightly different. So, okay, you should compare you should look at the dashed red line. This line here as a unit. So this is the prediction of general relativity. So you see, like if the black holes that we had were following general relativity and were circular, we would have this prediction. But then people found that the posteriors had this form. So you see, they are a little bit displaced from the naive prediction of general relativity, and they would point, let's say, to some smaller bounds. So they will point like to a flatter spectrum in a sense. So gamma should be smaller, so the spectrum should be a little bit flatter. Then they said, okay, maybe this is expected because binaries are not circular, so there can be eccentric, and these can be deviations. Maybe there is some interstellar medium. So there are things that can happen, and so this can be modified. But then they looked at the correlation between different pulsars. Okay, and they found the expected angular pattern that I was mentioning to you before, and it's quite satisfying. The reason people have not claimed a detection is because they haven't detected these with 5 sigma precision. They have detected it with kind of 4 sigma, so they have not claimed detection. But it's a strong evidence that really what we are looking at is a stochastic gravitational wave background. Of course, when I say stochastic gravitational wave background, I'm not meaning that this is coming from supermassive black holes. This is just a stochastic gravitational wave background that is propagating. People think it's coming from supermassive black hole binaries, but it's not something that you can infer from it.
So the black line is a prediction?
Yes, the black line is this thing here. The prediction of the angular correlation that you have in general relativity.
Anyone think that formula
Yes.
is very complicated? So someone will write the formula.
Yes.
So sometimes.
Yes. A lot of time. Yes. Yes. The formula is. I mean, the formula is. When you see it, it's not super huge, so it's like a compact formula. But to derive it, yes, it was complicated because it involved some kind of. Huh?
When was it derived?
When? I think in the 80s by Hellings and Downs.
Ah, okay.
Yeah, this is the Hellings Downs formula. So yeah, I think in the 80s, but I can check. So yeah, what we are looking here is like the basically what you do is you take two pulsars, you construct the correlation of the timing residual, and you find a number in this plot.
So the two plots are the ones for
Exactly. Exactly. So basically, you see here there's a number of pulsars that have this specific angle. You just look at the correlation, find a number, you put there, and you do it for the next pulsar, and then you can construct your value plots. But so it's not yet a discovery, but soon there will be the international pulsar timing array combination of data. So basically, people from the European pulsar timing array, from the Chinese pulsar timing arrays, from the North American one, etc., will combine all the data, and is expected that something better will happen. But okay, the title of my talk was about dark matter and modified gravity, so I want to talk about dark matter and modified gravity. And so I'm gonna start with ultralight dark matter. And the idea is that usually, I mean, we see that there is an amount of matter which we cannot really account for with the baryonic physics. This dark matter, non-luminous matter, interacts gravitationally, and it was thought that basically this dark matter was in the form of weakly interactive massive particles. So these particles should be huge, and then people try to build an n-body simulation to see how these particles form galaxies. And basically they found that, that the cold dark matter paradigm has some well-known issues. These are some of them, which basically all have to deal with the fact that looking at n-body simulation of the cold dark matter, there seems to be too much matter on the galactic center. And moreover, not only there seems to be too much matter on the galactic center, but the density profile of the dark matter at the galactic center seems to be a cuspy density profile, while we expect something more flat. We expect cores because we see cores. So people try to think, they started to question, well, how is it possible that we see cores, but we predict cusps? We see less density, but we predict much more density. And one answer was that there was baryonic physics at play, which was not accounted by n-body simulation. For example, I don't know, gravitational steering by supernovae. So supernovae explode and they modify a little bit the structure of the gravitational potential. But then in dwarf spheroidal galaxies, the situation is a bit more difficult because it is not expected that these dwarf spheroidal galaxies have a huge baryonic activity at their center. So invoking baryonic physics to solve these mysteries can be a little bit challenging. So people just said, okay, let's invent another dark matter candidate. And this dark matter candidate needs to have some special properties. In particular, it must be so light, of the order here of 10 to minus 22, but even lighter, so light that the Broglie wavelength should be galactic-sized. So you have to imagine a particle which is so light that the corresponding wavelength is of the order of kiloparsec. And in this way, if you try to take these dark matter waves and like compact them into the galactic center, well, you cannot do this because these are basically waves. So they will try to push. You cannot compress them too much. So basically, you kind of solve the problem of why you would expect cores. You see cores but you expect tasks in n-body simulation of all dark matter. Here we are changing the dark matter candidate, and we see that we can reproduce what we observe. We can reproduce for the profile. And then if you do the computation, this ultralight dark matter can be modeled as a scalar field, which has a huge occupation number. So you don't really need to model it quantum mechanically. You can model it as a classical wave. And this classical wave has a particular period, which is set by the mass of the dark matter particle, and an amplitude, which is, okay, as a contribution from the mass, and also it's set by the local density of the dark matter. But then in this formula, there is another piece, which I have not described, which is this phi hat. And this is a stochastic parameter that arises from the fact that these dark matter candidates are really waves. They are not particles. And indeed, when you try to construct simulation of how these really form galaxies, you see that they don't form a smooth profile. So they kind of form like clumps. So the density profile is like a clumpy density profile. And the size of this clump is roughly set by the de Broglie wavelength of the scalar. So you have to imagine as if like this scalar field have a de Broglie wavelength, and that sets the coherence scale of the scalar field. And so the dark matter density will look a little bit like this. It will be like patchy. It will not be smooth and continuous, but it will be like patchy. So the stochastic parameters phi hat that I showed you before arises really from this. Maybe you are in this region of the galaxy, but maybe you are in this other region of the galaxy. So depending on the region that you are in the galaxy, you can experience a different density of this dark matter candidate due to the fact that this dark matter candidate is a wave, basically. So a little bit the idea behind constraining ultralight dark matter with Pulsar Timing Arrays is the following. Basically, if you compute the time scale associated with the mass of this particle, so you just take mass to the -1 and you compute this time scale. This time scale is of the order of 10 years, 15 years. So basically, you have to imagine as if you have a wave, as I showed you before, with a specific amplitude and with a frequency set by the mass, and this wave is oscillating with periods which are long, like 10 years, 15 years. When you have a wave which is oscillating like this, you can do some computation, and basically you can see that it affects somehow the gravitational potential that you have in your galaxy. So when a beam from a pulsar is traveling in order to arrive to us, it will somehow experience the fact that this wave is changing. It will experience the gravitational potential caused by this wave. And so if we look at it today, it might arrive at some time. If we look at it in 10 years, it might take a little bit less or a little bit more according to where we are in the phase of that wave. So the idea is that this oscillating scalar field will produce a characteristic pattern in the time of arrival of the beam at Earth. So we computed this. Basically, it has this form. And there are 3 limits. I will not go into detail, but they basically have to deal with what I showed you here. So basically, if the dark matter is sufficiently light that we all live in one single bubble, we are in the so-called correlated limit. If it's instead larger than that, we have the uncorrelated limit, and so on. I can expand on this, but I will go on now to making this clear to you. Okay, so we did this, and we put this delta T that I showed you here, so the timing residual. We put this in that matter, the PTA pipeline, and we found some constraints. Let's look at the right plot. We found some constraints on the dark matter density. So the way to read at this plot is that this is an upper limit plot. So basically, the way to read it is that if you imagine that your galaxy has a dark matter mass of 10⁻24 electron volt, its density can only be roughly 30% of the observed dark matter abundance. Because if it was more, if it were more than 30%, then the effect that we computed would have been seen in our data. So the idea here is that particles with this light mass cannot really exist, cannot really, let's say, be 100% of the dark matter that we have in our galaxy. And if they exist, they can be at most 30%. This is kind of a robust result because we really did not do much. We just computed the expected timing residual due to a gravitational interacting dark matter. We did not really do anything fancy in there. But then you can say, okay, the previous result holds for a gravitationally coupled dark matter. But then what happens if you also put some coupling with the standard model? You might ask why you want to do this. My answer would be why not, as good as it sounds. But the idea is that we don't have really any idea about what dark matter is. So let's see if we can get at least some information from this experiment. And the qualitative understanding of the main point of of the following part is the following. If you have a coupling to matter, basically this coupling to matter will couple, or this scalar field will couple also to the matter in the neutron star. So basically, you remember this scalar field is oscillating. So what will you have is that the moment of inertia of this neutron star will also change with a time scale which is similar to the time scale of oscillation of the scalar field. And by conservation of angular momentum, if the moment of inertia of the neutron star changes, then also the spin frequency of the star changes. So the idea now is not really to see an effect that is in the propagation of this beam, but here the idea is that the pulsar itself is spinning at a slightly different rates. And so we can look at the data and we can try to see if there is such an effect. So
this oscillation.
Yes.
Settle down.
No. No. It's really a classic way of oscillating like this. No, I mean it's yeah. When you write so in galaxies, basically you can write this scalar field, and this is in principle you can write it as e to the I omega time minus k over x, okay, times x. That k sets like the set by the dispersion velocity of the dark matter. Basically, it's a typical momentum that it has. But the cosine wave that I'm showing you, it's really given by the mass of the particle. So it's not really something that you dump out. It's like when you have a free scalar with a specific mass.
Okay, but so when I think, for example, of an electron in the hydrogen atom,
yes,
that's somewhat similar. We have the quantum particle in a gravitational potential.
Yes.
But for the electron, I can only observe like the square of the intensity, which is no longer time dependent.
Okay, I see what you mean. No, but here indeed, what you can observe is the square, what you're calling the square, and that's the density. So here you see the square of this is roughly the density of that matter. But what I'm saying is that the presence of this oscillating scalar field, when you like write Einstein equations, and you have like a g mu nu equal to 8 pi t mu nu, then there it can produce an effect on the Newtonian potential, basically. So you can have an effect there. So it can slightly modify your metric in a sense. So this is yeah. In that, I mean, the square is the density, as you're saying.
Yeah.
But when you write here Einstein equation, you can expand the metric, and you can find that the Newtonian potential do have a dependence on the frequency.
So, but then in that sense, you also have to make an assumption. So don't we have to make an assumption how sort of quantum mechanical averages play out for the electromagnetic data?
I'm not sure yet. I mean, the way it's commonly done, at least, is you can say that there's a, there's really in the galaxy a lot of particles occupying the same state. This is like really a Bose-Einstein tendency. What I showed you before, those patches were a Bose-Einstein tendency. And you can basically describe them, this Bose-Einstein condensate, as a wave because they are like coherent. And then you take that, then you take that classical field, and then you use that for the Einstein equations.
But then I think, for example, of boson stars, so they're also sort of wave solution,
yes,
right? But they are static boson stars. They're just sitting there, not oscillating. Because the electromagnetic tensor does not oscillate, but the field itself oscillates.
Yes. But in that case, I don't think for like, I don't know how it works for a boson star, but I think you solve like a Schrödinger Poisson equation or something like this. No? Like so you are not really caring about this oscillation because you are solving for the, I mean, you're expanding your field as e to the I m t plus some times some relativistic correction. You're solving for that correction. So the equation that described by Boson star, I'm not an expert on Boson star, but you are not really dealing with this cosine part that I'm showing here. You are just dealing with the non-relativistic approximation.
No, okay. Boson stars are relativistic, fully relativistic stars.
Okay.
So the relativistic kind of relation.
But then you don't make any assumption. You just take that. You don't make any assumption.
No, I mean to construct them, then we say you want a static solution.
Okay. Yeah. So you can. So I think you can do this with a complex scalar field. No, the boson stars that are time independent, you can. But if you have a real scalar field, which is the case here, they depend on time. You cannot construct static boson stars, and this is the same thing here. It's a real scalar field, so. The metric has some time dependence, which is the oscillation he's talking about.
Okay.
Maybe if you want later, you can.
Yeah, maybe we can.
Is it the way it's done for boson star, and maybe I can comment.
Yeah, maybe we can.
Yeah, now I don't have.
So then my question would be why the assess here real.
Just assumption.
For example.
I mean, as
quantum mechanics, every scalar field you can describe as complex scalar field.
Well, I mean, here you can say it's a scalar, it's a real scalar field because I mean you just take 1 degree of freedom more. You don't have. If you consider a complex scalar field, it's like you're adding 2 degrees of freedom.
Yeah.
With your Lagrange, right? So here we take a minimal setting. We just describe it as a real scalar field. It's not really a reason. It's not really anything. No, it's not fundamental reason. I would say just like a more economical. You say it's not complex. But then in quantum mechanics, you really do are not relativistic approximation. Like the Schrödinger equation. Yeah. And then you can really write this scalar real scalar field. You can write it as complex, like as phi. You can write this phi as psi e to the I m t plus complex conjugate. So like if you focus on the non-relativistic part, which is this psi before, then that's a complex. That's complex. So in quantum mechanics, you deal with a complex scalar field for this reason. But here we are not doing really quantum mechanics. Yeah, I don't think it's in contradiction.
So I also think that complex, you might need a complex scalar field to construct something like a Pulsar charge for your field. Like maybe you want to. No. I missed a year of research. Okay. You know.
Okay. So, right. Okay, I was here. So basically, the idea here is that dark matter is a little bit more differently. It's not really minimally coupled gravity, but it couples to all the standard model particles through this factor here. So the way you have to think about it is that all the standard model particles, they now experience universally the same dark matter field. So all the standard model particles, which are in this psi m, they now couple not to G mu, but to this effective negative. And basically, when you start with theories like this, the main point that you want to compute is this sensitivity, which basically, phenomenologically, this sensitivity tells you how the spin frequency of the neutron star is affected by the presence of a scalar. So they tell you how this varies when this varies. This is information. So we really take these sensitivities from Adrien's code that has been used to do the work in scalar here. And we invert this relation and we find how this the spin of the neutron star changes for a given sensitivity and for when the asteroid is present. And the relevant quantity is this alpha here, which is the ratio, which is this ratio here, and A is this conformal factor. So like we can compute how this thing is spinning differently, and then we can say, okay, we do this computation, and then we specialize two cases. One case is where A is given by this factor here, and another case is where A is given by this factor here. These are two classes of modified of scalar theories. This is like the first Jordan does D class. This is the Moore-Esposito of arrays. And yes, so we compute again the timing residuals, and we try to constrain this time the presence of this coupling alpha here and of this beta coupling here. So you see, if this A was completely equal to 1, we would really go back to the previous case. Now we are saying, okay, let's see if there is a minimal interaction. And we find these results. I'm going to just focus on the left one, with the right one, with the beta. And basically, we find that we can constrain this alpha, not really this alpha, but the combination of alpha square root of density. These are the constraints. And these are very interesting constraints, because in this region, the only constraints that the most robust constraints that we have are the one coming from Cassini space definition, and they lie at -3 in this plot. So really, we have a huge amount of improvement by using pulsars in this mass range. So basically, that's it. And one can say, okay, let's now imagine that this matter candidate has a coupling with the standard model, so a generic coupling, and you can play the same game. Basically, I will not more details, but you can define your favorite Lagrangian, which is describe the interaction with your dark matter with the standard model. Then from this Lagrangian, you can compute the timing residuals, which is the quantity that is relevant for PTAs. And you can use the PTA pipeline to constrain it. And as you can see here, basically there's this bound super good. With PTAs, you can constrain the coupling of the electron in this form, and very robust way, much more than with other experiments. So with this, I conclude the part on by dark matter. I will drink a little bit of water. If you have any questions, please ask.
From the change of the period of the pulsar, from the expected one to the pulsar.
Yes.
That's correct?
Yes.
I check.
Yes.
Too small.
Yes.
And you want to have models that explain this small, extremely small difference.
Yes.
You need to have an extremely precise experiment.
Yes. Yes.
This is not the timing that requires that allows you to get some information reliable for one.
So is your question about how we can have such so precise? Maybe we didn't get it correctly.
Yeah, so yes, what is the precision that you need to have
Okay.
in your time interval
Right. Okay.
to be able to say that there is some precision there?
Okay.
This is not just within the errors.
I see what you mean. So basically, probably your question can be addressed by going back like this.
Yes.
So basically,
Before.
yes, maybe let's stick with this one. Basically, your question can be rephrased in this way, probably. Like, how precise should this equation be? I mean, which is the precision?
Error or millisecond.
Exactly. But the error is not on milliseconds. So basically, what you do is you observe this pulse for like 20 years, and this pulse is like sending you a beam each millisecond. So then you can construct your timing model here, and then you can really develop a fit. So you can say, okay, I have a fit that predicts when the next beam is going to arrive, given all the information, all the data that I have collected. And this fit, as of now, is good at the level of 10th of nanoseconds.
For that one.
Yes.
Okay.
So this, that's the goodness of this fit. So it's much less than a millisecond because I really observe this for a lot of time. So then I have a lot of data. And I can predict the next beam with an accuracy of 10 nanoseconds, maybe a little bit more, but roughly speaking, that's it. Okay, so here I will talk about a little bit how you can modify. You can constrain the presence of modified gravity with Pulsar Timing Arrays. I'm not a huge expert on this side, so I will present just my naive understanding. If you have any questions, of course, you can ask me, but then if I don't know how to answer, you can ask either this guy, Ludovico Capuano, who's a PhD student in SISSA, and he's almost finished as well, or this guy here, Pulsar, that I think most of you already know. So basically, the assumption that we will be making in this section is that the stochastic background is produced by supermassive black hole binaries. So if you remember, I told you before that we don't really need this background to be produced by supermassive black hole binaries to explain what we are seeing. We are seeing a stochastic gravitational wave background. And this is what Helix-Downs correlation informs us about. But it does not inform about where this background is coming from. So people, of course, expect that this is coming from supermassive black hole binaries in the universe. And I would also say that most of the people working on other interpretation also agree that actually it's from supermassive black hole binaries. But in principle, we don't know. And this is an important distinction that we make. So this background can be produced by other stuff. And here we will make this assumption that the stochastic background is produced by supermassive black hole binaries. So two of these big objects that are inspiraling around each other and emitting gravitational waves. So in the following, I will focus on a Gauss-Bonnet-like theory, which was developed by Astrid and collaborators in 2023. We basically took this theory and tried to see if there is an effect that we can see on pulsar timing. So I will provide you with a shameful introduction on Gauss-Bonnet theory because I don't really know much about Gauss-Bonnet theories, but this is my understanding, and I think it will be sufficient to understand what's happening after. So the idea is that in general relativity, we have no-hair theorems. So we have these theorems that tell us that a black hole solution is described sufficiently, it's only described by its mass and its angular momentum. However, if you construct a modification of general relativity, like the Gauss-Bonnet theory, you can show that this Gauss-Bonnet theory violates some assumptions of the no-hair theorem. And so the no-hair theorem really does not work for this theory. And therefore, you can have a non-trivial scalar profile around black holes. In a sense, the black holes will not be described uniquely by M and J, but they will also be described by a scalar charge, so another term, which is related to the scalar. The idea is that you take, so in Gauss-Bonnet, you have a form, an action which has this form. You have the usual term that you also have in general relativity. Then you have a scalar field, and the scalar field this time is coupled non-trivially to the metric. So it's coupled to the metric non-minimally through this Gauss-Bonnet invariant. So this is a little bit, this is the modification of invariant 32. And you see that before this term there is this lambda. This lambda is a length scale, which really is, I mean, it's real length, it's meters, kilometers, you can put what you want. But it tells, basically, in an effective field theory perspective, it tells you the scale below which you expect modifications given by this theory. So we can take this action, we can write equation of motion for this action. And then there are two cases in literature. The first case is when this f prime of phi is always different from 0. And you can show that in this case, no GR black hole exists. Basically, no black hole like this exists. The black holes are also characterized always by a scalar charge. And then you can consider another class of theories where you have a particular value of the scalar field with phi 0, in which f prime is equal to 0. So basically, if you put it here, you see that the scalar configuration will be trivial. So in this case, you might say, okay, the GR solution exists because the scalar configuration does not interact with, does not do anything with my black hole. But then you can wonder, okay, is this stable? What I mean by stable, I mean, it's okay that there is a solution like this, but then if I have like a small perturbation of this scalar field around this value phi 0, is this small perturbation stable? So is it gonna give me a GR black hole, or is it unstable? So is it gonna provide me with a scalar cover? And the idea is that for some values, you can write the Klein-Gordon equation for the perturbation this time. And the idea is that if f second g, if this effective mass term here is negative, then this perturbation will be unstable, and the black hole will develop a scalar hair. It's called the hair, and therefore, yes, this is the condition. So if we have this condition, more or less, not exactly this, but if this is necessary condition, if we have this, we will have scalarization of the black. But as I told you, in this theory, scalarization is like a threshold mechanism. So basically, in an EFT perspective, if you go like a length scales, which are smaller than this coupling lambda, you expect deviation from general relativity. So I might just look at the smallest possible black hole, and this will constrain me lambda in the best way possible. So if I look at a small black hole and I see that this small black hole has no deviation from general relativity, then there is no reason to expect that the huge black holes will have this deviation from general relativity in an effective field theory perspective. And this is a little bit of a problem because actually there's a huge constraint on scalarization from stellar mass black holes. And so, I mean, why should we even care about the possibility that supermassive black holes, which we are concerned with, can be scalarized? Why should we even start to think about it? And the reason why we started to think about it is that in 2023, there was this paper by us that came out. And basically they're saying, okay, you are claiming you are in an effective field theory perspective, right? It's okay. But if you are in an effective field theory perspective, you cannot stop at the first term here in this series. In an effective field theory perspective, once you are approaching the coupling scale, then you should also consider higher order terms. And so they say, okay, let us consider this term here. So a term goes like Gauss-Bonnet squared. And if you now write the equation of motion, you will see that the effective mass will be negative, but not always, but will be negative only in a specific window of masses. Basically, because these two terms have different signs. So you will have just a window of masses where your black holes are allowed to be scalarized, and outside this window of masses, your black holes will not be scalarized. So it's possible, completely possible, to have supermassive black holes scalarized, but stellar mass black holes not scalarized. And this is basically this is what we refer to. We take this theory, we develop some phenomenological fits for the scalar charge of the black hole relative to the mass of the black hole. So basically, this is not exactly what they have. This is like a phenomenological interpolation from the result. And basically, this tells you that depending on the value of this coupling parameter, which is this one normalized to a specific scale, you can have that only a certain window of black hole can be scalarized, while the black holes that are outside this window are not scalarized, so they are just behaving as a pure general relativity. So we start from here, but before going on, I just want to tell you that a few days ago, this paper came out by these guys here. By the way, this guy is also in this one, this paper here. And basically, they claim that this theory is not a theory that you can obtain from an effective field theory perspective if you start from an UV complete theory. Yeah, just take what I'm going to say with this with grain of salt. But the idea is that, at least my perspective is that we don't really rely on this theory here for having the result that we present. We rely on the fact that supermassive black holes can be scalarized. Now, if they can be scalarized because of this theory, nice. If they can be scalarized because of another theory, nice as well. We don't really rely on this. So, yeah. Lambda 9, yeah, it's not clear. Yes.
So what does this correspond to your
Yes. So basically the idea is that, as I told you, this is a length scale, right? So like as a back of the envelope computation, you can check that for if you fix the length scale to a specific value, the black holes that will be scalarized will be the ones for which the horizon is basically of the order of lambda 9. So it's basically the black holes whose size is lambda 9, roughly speaking. So this lambda 9 to us is normalized to 10 to the 9 solar masses. That's why it's called lambda 9. So it's a length scale, 10 to the 9 solar masses. We convert it to a length scale, and that's the value we normalize lambda to.
And in the actual, it corresponds to lambda or lambda period.
You're asking me what's this? This is.
I mean,
where does this play a role here?
Yeah.
It's not clear where this does play a role here. So basically, in this paper here by Alcom and collaborators, they have different phenomenological curves depending on the values of this lambda tilde compared to the value of lambda. We just take a phenomenological interpolation of their result. So this is not really related to a value of lambda tilde. It's like similar to the curves that they have for different values of lambda tilde. But it's not really, you don't really see it from. So in this sense, I was saying it's like a phenomenological extrapolation of their result. But in their theory, this is related to the form of these specific curves.
So you said also in this iPhone 2023 paper, they said that you have to include higher order times.
Yes, yes.
So, but isn't then don't you also reach the regime where you need all the terms because of motivation?
Yes, yes, I completely agree with you. I mean, I have no objection to this. I think so as well. So yes, in principle, you can always say, I mean, they did a proof of principle in a sense. So they did, okay, all the studies that you have been doing with Gauss-Bonnet theory, you have to be careful because when you approach the coupling scale, things can dramatically change. And so they proved this as an example. But of course, I don't think they claim that that's the ultimate theory. Indeed, what they do in this paper here, they start from a UV complete theory and then try to derive the effective field theory. In this approach, probably, I mean, if one is able to prove that higher order terms do not exist, then okay, this makes sense. But as of now, I agree with what you're saying. Yes, it's correct. So I'm gonna go on. It's almost finished. So basically, the idea is when I have a scalar charge, is that now I also have some kind of interaction which is caused by the presence of this scalar pair. So this scalar pair, like in electromagnetism, and you have two charges, basically, and this is basically what's happening. So when these black holes are very, very far from each other, which means when this x is very, very small, from general relativity, which is this contribution here, you would expect that the frequency evolution should be super small. So these black holes are super far away, and they take a lot of time to get close to each other. But now, since they have a scalar pair, they can sweep more easily through the evolution, because you see that there is also a distance here. So at some point when x is very small, the scalar contribution will kick in. And so basically these black holes will not evolve according to general relativity, but will evolve faster according to this modified gravity theory. So keep this in mind, because this is basically the idea that allows us to use Newton as a prediction. And the idea is the following. This is basically the analogous of the power spectrum that I was showing you before in one of the first slides for a population of supermassive black holes. Basically, the way to understand this is like the energy that a binary emits in a log frequency beam. So the energy that it emits while it varies a little bit, while the orbit varies a little bit. And this is the number of binaries with those specific parameters. And then I integrate over all of these. So the way I'm doing this, I focus on a binary with some specific parameters. I compute this quantity here. I multiply it by all the binaries that have those specific parameters, and then I integrate. Basically, if you compute this quantity is, you can write it as d over dt times dt over d dot x. So if you remember from the slide before here, you see that the f in dt, which basically is the inverse of this quantity here, is modified when we are in general relativity. Is modified in this scalar in this Gauss-Bonnet theory with respect to general relativity. And the idea is basically what is happening is that, as I was telling you before, these black holes will sweep faster, will inspiral faster because of the presence of this scalar pair. So they will not spend as much time as they would have spent in general relativity on a specific frequency. This is why in general relativity you get this nice prediction, which is the orange line. In this theory that we are considering, you get this green prediction. You see, at low frequencies, the black holes are sweeping faster, so they do not stay in a specific bin for enough time, for a long time, let's say, and so you don't manage to build up to general relativity, because you're just sweeping faster. As you can see, the spectrum is slightly modified, so we just take this spectrum and we feed it to PTA data. And what we find, just focus on this part here, we find that basically there seems to be an excess in PTA data, and we find a preference for a specific value of this lambda. In other words, we might say, wonderful. This is a proof that supermassive black holes are scalarized, because the scalarization of supermassive black holes really tells us is more in agreement with data. So you can be excited, but it's not really this way, because we are not entirely sure of what's going on, because there's a lots of physics that can produce this. So this effect can be produced by eccentricity, for example, because also when a binary is eccentric, it will inspiral faster than the circular prediction. It can be caused by environmental effects, because also in that case, you can inspiral faster than the GR prediction. So you cannot really draw a definitive conclusion. But what you can say is that in future data, future data will be supposed to give us a very much better handle on the astrophysics of around supermassive black holes. So once you know a little bit better the astrophysics around supermassive black holes, then you can really disentangle the effects, and you can also be able to test fundamental physics. In a sense, what you can say so. What you really measure with PTAs is that if let's say if GR was, if circular binaries in GR were the answer, you would measure a characteristic strain like this, while instead a characteristic strain like this, the green one, seems more compatible with data. So yes, this would point to black holes that are inspirally faster than in GR. So yes.
I have a question. This in general applies whenever you modify one. But in situation modify one, you have this gravity unequals to gravity check. So you consider to modify the theory, doesn't the photons it observed from the pulsar totally different?
Yeah, this is a good point. So basically, the way that this particular theory of gravity works is by scalarizing supermassive black holes. But as I showed you, that there's a window of scalarization. So supermassive black holes will be scalarized and not else. This means also that pulsars will not be scalarized. So the way that they emit will be is in pure physics. They will not have any effect depending on physics. And then the scalar field that we are considering is not coupled to matter, so that also does not have any impact on the photon beam. So in this specific, what you're saying is correct. In this specific theory, does not apply because of these reasons, but it's correct. So yes, this is my final slide. So I think that PTAs are extraordinary experiments because of the potential to unlock astrophysics. But it's also, it's also true that they can give us a lot of other information on other stuff, fundamental physics. And I hope to have convinced you that they can be wonderful probes of ultralight dark matter, and they can also tell us some information about modified gravity. So thank you very much for your attention.
Any questions?
So, towards the end, you said there are all these different effects, but basically make it difficult to make conclusions. So, are there any ways to disentangle different effects?
That's a good question. As of now, I would say it's a bit difficult, but like in a few years, we're gonna have the combination of all the data from Pulsar Timing Arrays. This will give us like a better handle on the underlying physics. So maybe in this way, yes, you can have some more information. I'm not sure if observation, like in some frequency band, can tell you. These I'm really not sure. But yeah, the idea is that you need to know some more things about the environment. With future data, you're expected to know some more things. But yes, it's a good question. I don't know to what extent. Yes.
What do you mean by environment?
So basically, when there can be, I don't know, probably a certain binary list around these inspiraling supermassive black holes. Probably some interaction with stars, although that's expected to happen a little earlier. Yes, I would say, yeah, circumbinary disk, gas accretion, this kind of stuff. Huh? Yes, yes. Basically, I mean, this prediction here, the orange line holds if you really are in a vacuum and these things are orbiting. These supermassive black holes are spiraling in a vacuum. But I mean, you expect these supermassive black holes to form after the merger of two galaxies. So it's not really immediate that there will be a vacuum around them. Probably they will be spiraling and there will be a lot of matter. So yeah, that's what I mean by environment. Yes. Yes, indeed, I did not specify this. Thanks for the question. This is probably the cosmological model you're referring to, right? So this is like the number of black holes with specific parameters. And this is, I mean, this is a formula that interpolates among a lot of results from semi-analytic codes. And these parameters are not fixed, they are varying parameters. So we let them vary in our analysis, and we see if data have a preference for these parameters. And indeed, from the corner plot that I showed you here, and okay, it's not clear because it's very small, but n dot that I showed that it's here, it's super well constrained. It's quite constrained. You have like a good determination of a dot. This gamma also, I mean, it's not constrained, but you can see that it favors high values, or it disfavors low values, and the other parameters are basically unconstrained. So, yes. So in this sense, we do an agnostic analysis. We let these parameters vary, and we see what data tells us.
So I think all the results came from here are sort of for the statistical average on the population of sources, right?
Yes.
And the PTA, is it also possible to measure based from a single source?
Yes, it is possible. Indeed, it's like something that people are doing now. There is not yet an evidence that you can. We have not really seen yet a single source, but people are working on it now. What I'm showing, I'm not sure it will hold because in order to see this modification of gravity, you really need to look at the integrated population, because if you look at just one binary, it will not evolve during your time scale of observation, right? You can look at it for 20 years, it will be completely monochromatic during 20 years. So there is no way you can see, it's spiraling faster or slower. It's not really can tell. So for this analysis, the fact that we measure continuous gravitational waves or not, we measure single sources or not, does not really help. But in principle, yes, you can measure them as well.
So, and I have another question that goes towards the beginning of your slides. When you were talking about all these different contributions, and you said there's a solar wind contribution.
Yes.
So, I mean, it's not really the topic of your talk, but I wonder whether you know how we get the solar wind contribution.
What do you mean how we get?
So we measure the solar wind on Earth, and then we say we assume that's the solar wind everywhere.
No. I mean, there's a model of this solar wind. I'm not sure how it's developed, the model, but there's a model of how this solar wind behaves. Then, depending on the position of the pulsar with respect to the sun on the sky, and on the line of sight of the pulsar with respect to you, you can like model how much this pulsar is affected by the model of the solar wind.
But the solar wind must be entirely independent, right?
This is a very good question. So in PTA, it used, I mean, in early timing analysis, solar wind was modeled in a specific way, and then there was, I think, just one fittable parameter. So basically, you have observation, and you model the solar wind in terms of stuff, and you have one fittable parameter in this solar wind model. But then they discovered it's not enough. They discovered that the variation of the solar wind can be actually much more complicated. So basically, the way that they do now is that they don't have like a fittable parameter, but they have many fittable parameters. And they fit many parameters to data. In the end, it's not, I mean, you can say it's not super satisfying. I agree it's not super satisfying, but in the end, what you really care is to measure things at the 10 nanosecond precision level. Once you are at that level, it's okay, even if you don't really understand what's going on, I guess. Then if you really want to go better than that, then you should understand. But yeah, solar wind is really actually, it's really a thing that I think should be modeled way better than stuff, yes.
If you enjoyed the video, like and subscribe.